physical modeling and trying to summarize what we are doing here. And first, several words about MarTe project and why we are trying to collect all people together here. So MarTe is a maritime technology excellence hub in sustainable blue economy in the Baltics. So it's a project, but we would like to make it sustainable and make after the project community which works together. And our mission is connect science and innovations and support the improvements of the maritime environment, efficient use of resources, and the development of sustainable blue economy. And this includes everything related to Baltic Sea, coastal regions, ports, and industry who working on these fields, and people who live here, also local authorities and institutes and universities who are trying to do some research and innovations in this field. Project started in 2025, and we're going to organize at least 3 similar workshops for scientific dissemination and show how we can do science and how the science could be useful for our industry partners. And in this case, 1 second. So MarTe, it's unite a so-called quantiple innovation helix framework, which collects academia, industry, government, civil society, and environment itself as a wide partner. And this is 2 countries, Latvia and Estonia. Together we are 13 partners, civil society like a Baltic Coast, Worldwide Fund for Nature, Estonian Iceland Cooperation Council, public authorities like Environmental Investment Center of Estonia, Saaremaa Development Center, Kuurne region, and Latvian Investment and Development Agency, and supporting with research from Tallinn University of Technology, University of Tartu, Latvian Institute of Aquatic Ecology, and Ventspils University of Applied Sciences. So we are here, and industry and business partners and stakeholders as well, the Estonian Maritime Industry Association and Ventspils Seaport Authority. And so how we can combine all together and how we can boost research groups to communicate with industry and understand what industry partners need and how research could help to make a new deep take products in this case. And probably in this day we speak a lot about technologies, but it's good to understand what is technology itself and how it could be developed, and basic principles of technology readiness level. You can see it here. Try to make it laser pointed as well. So we need some ideas, and when we have idea, first of all we need to define it and make some first assumptions. And we could achieve basic principles observed, so some preliminary studies, feasibility studies, and we got to L1. Going next, we need to test this idea. Is this working or not, or it's maybe completely impossible to do something? And we formulate technology concepts and make some first laboratory tests and some first models, maybe on paper, maybe on computer, maybe sitting in laboratory technical benches. And when we are finished our research or make us like an experimental proof of concept, we somewhere in research level 3, and this is mostly institutes and universities do this like a research proof of concepts. Next, we need to go and collaborate with industry and think how our ideal concepts could work in real world. And we need to make some kind of prototypes and test them in laboratory. And after that, validate in real environment. And usually here, so it's mostly researchers, but here we bring also entrepreneurs and industry who would like to use this technology in later stages. Next, when we are ready to say something, okay, we have a prototype is working as we expected, we need to make it some kind of, not product itself, but a prototype which operational in demonstrated in an operational environment in real life in this case. And after that, we can make our certifications and licenses, for example, if we need to move it to market. And this part is mostly related to industry. In this case, industry need to join this research and bring this efforts to bring this at product level. And if you divide, make it a real deadline and achieve a fully operational system, so we say, okay, our, for example, hydrogen compression system working as we expected, we can sell it. And this goes to fully industry and entrepreneurs who need to disseminate it for the later public. And when we're speaking about physical modeling, we are somewhere here, level 2, level 6. In different levels, we need different kind of approaches and models. And maybe first of all, I will say a couple words about Ventspils itself. So you are in Ventspils University, and in university, science related institute is Ventspils International Radio Center, do astronomical, radio astronomical modeling, and far beyond a lot of activities related to space and physics itself. And here is an example of some models and the real results. I show our telescope, 32-meter telescope, which located near Ventspils in Urbana, 30 kilometers outside. And when we start to develop some new instrumentation or new ideas, so we need, and usually we start with visualizing concepts, and it helps to do some 3D modeling tools. We can use these 3D modeling tools and print a prototype in 3D printers, and these give us like a first preliminary understanding what we would like to create. Later, in later stage, we need to add physics and analyze how physics-based simulations can be involved in this, our design. For example, here you see this is a like a vertex room of telescope. Here is one more, and inside is a cryogenic system which works in 20 kelvins, so it's minus 250 kelvins. So very dedicated system which have to work on moving conditions. So its telescope is rotating quite fast, and we need to analyze how this model not only smooth design and smooth result concept, but how it physically operates. And next, we need like a engineers and industry support to create this in a like a physical in metal. And using models, we can skip several steps over like a laboratory testing, trying to understand so how our model will survive under different conditions. And here, how it looks in practice, for example. So we have nice plot, which could be done rather easily, but could be not enough to understand if these, for example, transitions or heat sinks works under cryogenic conditions. So, and first of all, we need to make it drawings. After that, we need to test it, and after that, we can do it in metal and test it in laboratory in metal. And after that, proofing our physical model. And very often this is interactive process. So we're creating a prototype, find out what our model was not precise, and we need to adjust it, like I mean physical model of our vision. We adjust model, improve it, and given new results, and given we'll see new prototype in a metal. And physics itself. So how we can, what we can calculate using our models, and usually it's starting from structural mechanical, like a stress, strain, deformations, and fatigue and vibrations, which give us some estimate of our constructions. Next, very often we need to include heat transfer, like a conduction, convection, radiation, and thermal management, showing how our, let's say, engine or compression system heats in time. And this is sometimes very critical if you are not able to make a equipment which cooling down in particular temperatures, you probably will be overheated and system not working. Next, we're adding some fluid flows like gases and liquids, one or two or both. And very often we need to make like airflow simulations or water currents or turbulence and pressure losses. For example, if you are trying to build a wind turbine, so we need to make a analysis how this wind turbine will survive under different wind conditions. And one option, we can use wind tunnels, like a physical wind tunnels, which are good enough to test like a scaled models, but sometimes it's not completely enough to make proper understanding of 200-meter long blade, how it evaluates in different wind conditions. And we definitely need a model of this turbine in our SolidWorks or OpenFloor, for example, and understand how models could be adjusted with real conditions. Often, and we also use electromagnetic process like magnetic fields and forces and inductions and electrical forces, how they could be modeled. And here's an example of permanent magnet modeling again. So we need to understand how these forces influence of our strengths of our construction and works together with like movements and so on. And next step, we use multi-physics interactions. So we use several like physical things like a flow and heat, electromagnetic process and mechanics like a structure and thermal coupling. We need to model them and understand how our future best prototype will survive on different conditions. And in many cases, this is not a static process, but this is dynamic. So we need to find out transients and instabilities in our prototype in different conditions and how in real operation conditions it works. Next step, it could be when equipment is created, or let's say wind turbine is built, we would like to see how long it survives. And it could be so that we create a so-called digital twin, which lives same life as a real wind turbine, but in a digital form, and we can see how these structural changes in time, and if we see some kind of parts of this wind turbine need to be replaced in year time, we already know what we need to buy additional parts, for example. And some example of flow, that's like a compressor chamber, what we are trying to model, and in some kind of dynamical process of liquid and flow and air animation in one compression chamber, for example. And what we can see here, and some kind of different ways and different structures. So before we build a real thing, we can try different scenarios, find out best one, and like save time for prototyping and understanding of things. Yeah, so it's some kind of nice plot that could give us statistics and answers how this equipment works in real conditions. But now we're speaking about like a small scale instruments or models or prototypes, let's say laboratory testing. But very important about extend our physical modeling to ERC systems, to model a global process which occurs around us. And tomorrow you will see our colleagues from University of Latvia describing how we can also model atmospheric conditions and how this process works. And usually, so it's like a atmosphere, like a wind pressure, temperature, clouds, extreme weather predictions, ocean models which involve currents, waves, sea level, and temperature distributions. And actually, each of us use these models almost every day. So probably first in the morning, what are you doing? You're looking on phone and looking forecast for today. Is it cold? Is it raining or not? But behind this is a very complicated atmospheric and ERC models, which provides us forecasting data. And usually these models are extremely heavy for calculations, so it's not possible to just run it on single station. We need very dedicated clusters for it. And here, these models also give us like a short-term forecasting, let's say couple days, couple weeks, maybe months. We're looking also for long-term simulations, we're saying years and even hundreds of years, showing how our, for example, Baltic Sea change in temperature and saltness level, for example, and how our life changes during this period, for example. And this is, again, physical model, which not only complicated, but also could be not very precise. So, and probably you see forecasts for a couple months, and usually it's 50-50. It could be true, it could be false. And unfortunately, even our technologies at this moment not able to predict what will be after a couple months in our clean climate. So how it's, is it summer will be warm or it will be raining? Nobody tells you. This is some kind of variability, but not exactly precise. And for these models, usually we need high performance computing and parallel calculations. And going next, some examples of these models, which are models of oceans and atmosphere, actually a lot of and different one. Here's maybe some of the latest one, Copernicus Interactive Climate Atlas, and just showing how temperature rises in exactly northern pole. So we are suffering from higher temperatures actually in last 10 years, and it goes 10 years in future. So it's climate changes, and you can see it, and you can model how precisely. It's a good question, but it's a tool that we can use. And the same instrument, for example, new European Wind Atlas, which shows how wind resource could be available in a Baltic region. And here is yellow, so it's very windy and very nice for wind turbines. Bluish, it's more or less okay, but maybe not so good. And again, for this model, it takes like 30 years of modeling data. So it's models from 1985 up to 2020 somewhere. So it's modeled data, so about wind resource in complete Europe. And in size, it's around 80 petabytes of data. So if you just compare your hard drives in your computer is around, let's say, terabyte, 10 terabytes nowadays. Here is 1,000 times bigger data space what we need, and to store and analyze this data. And again, so scientists not only stopping on here, and maybe I will show you some video at the end of my talk. So how looks to model galaxy in millions of years? So it's a forming galaxy, and we could model not only small processes in a year, but it's possible to organize and model billions of years of evolution, and in distance of hundreds of parsecs. And this quite nice physical model. So again, completely different one. So we're starting from small prototypes and small physical models that we can use and to create let's say drone or vehicle. But there is something completely different. So it's physics which shows how galactic is formed. And yeah, so it's some kind of nice examples. Yeah, I think I will stop here because it's like a mostly introduction of what you will hear and see in next days. So we cover a long list of different and difficult topics of modeling effects of physics, what we can put in numbers in computer and work with them and see how it evaluates in the product. Yeah, so thanks, and maybe we have a couple questions, time for questions, and we'll change to participant view.